This lecture is going to cover the basics of how significant figures are reported within measurements. So the goals of this lecture are to learn the importance of significant figures in measurements and to learn how to determine the number of significant figures reported in a particular measurement. As a reminder, please look over your textbook, sections 1.4 and 1.5 of OpenStax, and don't forget, after you complete this lecture, to complete the short Canvas quiz. This continues our discussion in this course about scientific measurement and uncertainty and how this affects our understanding of the world around us. So, a little review. The last lecture you should have watched, we went over the importance of measurement and the importance of every measurement to contain a unit to go with the numerical measurement itself. And we also discussed how every measurement has some amount of error associated with it. Now we're going to discuss significant figures, which gives us a way of expressing that uncertainty within a particular measurement. So let's start off with an example. And the example we're going to start off with is looking at this graduated cylinder we have illustrated on the slide, and asking ourselves, what is the volume of water in this graduated cylinder? And we can think about this first. The first thing to remember, though, is when we look at measuring water, we're always going to measure the bottom of the meniscus, which is that curve of water from either side. And so when we look at the bottom of this meniscus, and start reading the volume, we can see, looking at the graduations, we are somewhere in between 1.7 milliliters and 1.8 milliliters. Um, so what we know for certain is we are above 1.7 and below 1.8. Whenever we record a measurement, we can always estimate one decimal place past the smallest graduation. And what I mean by that is we can look at this and say we're above 1.7, we're less than 1.8, that bottom of the meniscus is less than halfway between them, so I might call that 1.73 milliliters. Now, you might read that, or I might read it again and say 1.74, I might say 1.72, and that's just illustrating that that last decimal place, that 3, which is in red here, is the uncertainty of our measurement. That's representing where we are estimating that last piece of a measurement. So a couple other examples for us we can look at. Illustrated on this slide are a couple pictures. On the left, we have a beaker of a red solution, and on the right is a graduated cylinder with a close-up of that graduated cylinder. So if we were to record the volume of this, again, we'd look at the bottom of the meniscus, and for that beaker, we'd say the graduations are all in units of 10 milliliters. So we know we're above 30 milliliters. We're clearly below 40 milliliters. And again, I think that's a little less than halfway between 30 and 40, so I'm going to estimate that to be 33 milliliters. And that second 3 is, again, our uncertainty. Maybe it's 32, maybe it's 35, but certainly above 30. When we look at the graduated cylinder, we again go to the bottom of the meniscus, and in this case we can again see 31, 32, or a little below that 32 line, so I'm going to call this 31.8 milliliters. This liquid is the same liquid I poured into the beaker first and then into the graduated cylinder, and so you can see within error this is actually the same volume of liquid, just measured with two different pieces of glassware in the lab. These significant figures, also known as significant digits, indicate how precisely we know a measurement. And we can look at this and say the beaker gave us two significant figures, right? That means there's two numbers to that measurement, whereas the graduated cylinder gave us 3. We can be a little bit more certain of the measurement of that graduated cylinder because of that extra decimal place. So what we would say is the graduated cylinder is a more precise instrument than the beaker. Let's look at another example. In this example, we can consider the mass of a ruby. I have pictures of two balances, and let's imagine we go into lab and we measure the mass of the balance on of the ruby on the first balance, and we say that mass comes out to be 25.645 grams. Now this is a digital balance it's giving us, but there's still uncertainty in that measurement. If we take that ruby and we transfer it to the other balance, now the balance tells us the measurement is 26 grams. So, did the mass of the ruby change between balance A and balance B? Of course not. It's the same ruby, it has the same mass. What we're seeing is the difference of the uncertainty of the two balances we are using. In the first case, that 26.645, that's 5 significant figures, we're seeing the uncertainty is in that thousandth place of the measurement. Whereas in the right balance, this is somewhere between 25 and 27 grams. That uncertainty is in that first place of the measurement. So within error of measurement, these measurements are in fact the same, which we know they should be. The last digit is our uncertainty. That's what we're trying to express with these significant figures. So when we talk about our sig figs, they're going to tell us about the uncertainty of a measurement, and the number of significant figures within a particular measurement tell us how certain we are about the measurement. This is especially important for calculations. What happens if we combine two measurements that each have uncertainty? How is that uncertainty propagated to our final answer? So let's look at a couple examples of this. In the first case, let's consider the case where we're adding two masses together. And so imagine if you go into the lab and you measure out 631 grams of a substance. And then on a different balance, you measure out a mass of something, and it's 1.2932 grams. We could add these together, and mathematically, we would get 632.2932 grams. But does this answer actually make sense? Does this express the correct amount of uncertainty in our final answer? Think about what those first two measurements really are telling us. In the first case, that 631 grams, we can really think about that as being 631 plus or minus 1 gram, because that uncertainty is in that first position in our number. In the second case, we know that to be 1.2932 plus or minus 0.0001 gram. Now, if we add those together, what is the uncertainty of our final measurement? And what I hope you can sense from this is our uncertainty in our final answer has to be limited by our most uncertain measurement. So our final answer we would have to report as 632 grams, right? With an uncertainty of plus or minus 1 gram, because that's the uncertainty that got carried from our least uncertain measurement. All right, so when we look at our significant figures in a measurement, there's a set of rules to figure out how many significant figures are present in a given measurement. And the total number of significant figures is the number of digits recorded in our measurement. Sometimes this is fairly straightforward. The last digit is uncertain, so we can see something like 631 grams. We know this really means that quantity is in between 630 and 632 grams. We can also have things like exact numbers, 12 in a dozen, 7 days in a week. These have an infinite number of significant figures because there's no uncertainty. These are exact numbers. In other measurements, the number of sig figs is usually just the number of digits present. So 631 has 3 significant figures. If we had 42.85, that has 4 significant figures. And if we go to something in scientific notation, 6.5 times 10 to the negative third grams, this would have 2 significant figures. What gets a little complicated is when we have zeros. We have to pay attention to the location of a zero in our measurement. Anytime a zero is in between other numbers in your measurement, they're always said to be significant. So 2006.1 would have 5 significant figures. If, however, we have zeros at the beginning of a number, but after a decimal, they are not significant. So those first 3 zeros of this 0.0043 are not significant, and we'd say there are 2 sig figs. If the zeros are at the end of a number and after the decimal point, they are always significant. So take, for instance, the difference between 4.00 and 4. 4.00 has 3 sig figs, whereas 4 has 1 sig fig. And just think about that in terms of the error. 4.00 means the error is plus or minus 0.01, whereas 4 tells you the error is plus or minus 1. And finally, take the difference between 70 decimal point and 70. That decimal point after the 0 in the first 70 is telling you that that 0 is significant. So that could be 69, it could be 71, whereas in the second case without the decimal point, that might be 60 or that might be 80. Two very different measurements. So we have 2 sig figs versus 1 sig fig. Okay, so let's try a couple examples. So what I'd like you to do is take a minute, pause the video, jot these numbers down, and indicate how many significant figures are present in each of the following measurements. When you get your answers, hit play again, and we'll go over them quickly. Okay, so hopefully you took a second to come to some answers of your own. So in the first case, we would say that final 0 is not significant, so there are 5 sig figs. In the second number, 8.35 times 10 to the negative fourth, that final 0 is significant because it's after a decimal, so we have 4 significant figures. We have 13,000 kilometers. Those last 3 zeros, none of those are significant, so there's 2 sig figs. 12 envelopes. This is an exact number. This isn't a measurement, so this has an infinite number of significant figures. And then at our bottom row, we have 0.080. So in this case, we have 2 sig figs. The 8 and the final 0 are significant. 80 decimal point, again, 2 sig figs. 80 with no decimal point would only be 1 sig fig. And 8.0 times 10 to the first would again be 2 sig figs. All right. So one way to maybe help you when you're trying to determine how many significant figures are present is to think about numbers in scientific notation. For example, if you look at 2 examples, we'll look at a very large number and a very small number and how it can help us determine the number of sig figs by converting to scientific notation. If we were to measure the distance of the Earth to the Sun, that is reported as 149,600,000 kilometers. Now, we could figure out the number of sig figs from this number directly, but if you're ever unsure, just convert it to scientific notation. When we see it as 1.496 times 10 to the 8th, all of those trailing zeros go away, and now it's a little easier to see 4 significant figures. By contrast, we can look at the diameter of a hydrogen atom, would be shown here. Very small number. Again, let's convert it to scientific notation. And in this case, we get 1.20. Notice that final 0 stays because it's after the decimal, times 10 to the negative 10th meters. And it's a little easier to see 3 significant figures. So that wraps up our lecture on significant figures. What we still have to cover, and we'll do at a later date, is what will the uncertainty be when we combine 2 measurements, and also how do we convert units. A final reminder, don't forget to complete the short Canvas quiz after watching this lecture. Thank you.